evening, I was drinking my coffee, thinking about the consequences of my mistakes. A gloomy Thursday, without a colloquium, without even cookies in the afternoon. And suddenly walks in Paolo. And we start talking, and of course the conversation drifts toward dark matter and supersymmetry. And Paolo tells me, you know, Stefan, you have missed the turn. Supersymmetry is totally has-been. Tomorrow, no one will even remember about it. And then he made a mistake. He said, and by the way, I have an excellent talk about it. So at that point, I knew that the fight would not be long. And I had a speaker. And so he kindly accepted to give this colloquium on a very short notice, just yesterday afternoon. So let's welcome Paolo telling us about dark matter.
Thank you for the kind words. I don't know if the talk is excellent, but there's one sentence that Stefan said and convinced me totally that I should give the talk today. He said, "You cannot let us without cookies." So this is a presentation on direct dark matter searches for dark matter particles, and there's been a lot of rumors around and a lot of results in the past recent few years, and a lot of confusion with claims of detection and counterclaims that it cannot be. There's been a very dramatic story, and it is as a drama that I'm going to present it, like a TV drama, or those in the know, a Korean drama. I divided the talk into 4 chapters: the forbidden fruit, confusion of the mind, treason and murder, that which does not kill us makes us stronger. Are we okay with the lights in the room? Or do we?
It should be
I don't know, anywhere you wish. Can you read?
either way.
Either way. Fine.
I'm not sure it works.
Okay, don't touch it, it's bad. The forbidden fruit. Let me recap with the evidence for cold dark matter. It comes from many, many places, and you heard many talks about it, so be very quick on this. And we believe there is dark matter on all scales in the universe, from small galaxies up to the largest scales in the universe. The evidence comes from observation that galaxies spin faster or are hotter than gravity visible mass can support. You observe this through rotation curves. We measure using the Doppler effect. We measure the velocity of rotation of the gas around a galaxy, and we find that the gas is just simply too fast to be supported by the force of gravity. Just F equals ma, and it doesn't work. We measure the velocity dispersion in elliptical galaxies and small dwarf galaxies, and we find the same, that the stars and gas are moving too fast to be supported by gravity. They would fly away. Galaxy clusters were the first piece of evidence, perhaps, where dark matter was found. They're mostly made of invisible mass. We know this again from the motion of galaxies inside the clusters. They're, again, too fast for the gravitational field. We also measure the gas density and the gas temperature of the plasma in the cluster. And we measure gravitational potential through gravitational lensing. All these results more or less match. And when we find there is an additional invisible mass, Fitzwicky is one of the early proponents of invisible mass. And for some reason, you look at the picture, nobody believed him. Yeah, we were attempting to do that. So if you know how to.
Beyond my paper. You're not talking about dark matter anyway.
Better be in the light. An invisible mass also makes the cosmic accurate background fluctuations grow into galaxies. We observe this in the matter power spectrum, the correlation functions about the position where galaxies are. And after all these data are put together, as I said, it's a really short introduction to this evidence that I hope you got from many other talks in the past. We compile all the evidence into numbers using general relativity, statistical mechanics at a temperature of 10,000 Kelvin, when we believe we understand physics at 10,000 Kelvin. We're using linear perturbations, so this is linearized general relativity. We understand that, so we believe we understand everything, all the physics that goes in here. And these are the numbers we come up with in this cosmic pie chart of the observed energy content of the universe. In physical units of energy per unit volume, we have about 500 picojoules per cubic meter in what is called dark energy, some uniform darkness across the universe. 200 picojoules per cubic meter in cold dark matter, and a little bit of neutrinos, a few picojoules per cubic meter, ordinary matter, like all the chemistry, and some photons that are around, which create the beauty of the sky. Really, the question that I'm addressing is, what is dark matter? So we see this, but we don't have an explanation of what it is. Modified gravity, it is not, because we know there's a problem with symmetries. If we look at some clusters, like the Bulla cluster, the Bulla cluster has two potential wells, a central source, and there's no theory of gravity that can break a spherical symmetry and create two potential wells out of one central source. So that is really the hard part for modified gravity. So we are left nowadays with just dark matter particles. Is it an elementary particle? No, not a particle that we know already. We go through the table of elementary particles. It's not quarks and electrons, because that's ordinary matter. It's not things that disappear too quickly because we see it in the early universe about 100,000 years after the Big Bang. That's 13 billion years ago, so it has to be around till this very day. It cannot be neutrinos, because it turns out we nowadays know the mass differences of neutrinos. We have upper limits on their masses, and we could go through the physics of the early universe, and they constitute what is called hot dark matter. They are part of the invisible universe, but they are moving too fast to fall into galaxies, to form galaxies. So they're not neutrinos. There's nothing in this table of known particles that can be the dark matter. That's really the dark matter problem. There are many, many solutions. Physicists have even too many solutions, and I focus only on one today, which is I call the magnificent WIMP. Now, WIMP means a weak and cowardly person, and this is a magnificent cowardly person. This idea goes back, maybe should we try the lights again? Because this is a little, after our introduction to the dark now, to dark, I really, let me try. First row.
You see?
Oh, the power of darkness. So the basis of this idea goes back to the 70s by Zildovich, who appears in every cosmology idea, as a Russian cosmologist, and in the West, Lee and Weinberg. And they realized that there is a simple natural mechanism in which particles can be produced in the plasma, like electron, positron annihilation in the plasma can produce these WIMPs. And if one goes through the calculation, if the WIMP cross-section with electrons, say, is of the order of the weak interactions like neutrinos, one obtains the right cosmic density of WIMPs, and one obtains these 200 picojoules per cubic meter that we actually measure. This is called the thermal production in a hot primordial plasma. So this is just an idea, but the importance of this idea is it can be tested, because the same hypothesis that enters the prediction on the cosmic density of WIMPs also enters their observation. The same physical processes that produce the right density of WIMPs make the detection possible. So we're not talking about two different theories here. We're talking about the same physics, just looking at it in a different way. In one way, we produce these particles naturally in the plasma, in the early universe, obtain the right density. They are the cold dark matter. On the other hand, using the same physical processes, we can hope to detect them. So, a few short images. Here's the power of the WIMP. They're produced in the early universe, like two standard model particles here represented by two fermions, which should be an electron and a positron, or a muon and an anti-muon, or a quark and an anti-quark, would produce two WIMPs, or a WIMP and an anti-WIMP, depending on the WIMP theory. So this happens in the early universe together with the annihilation of these particles, the back reaction, and the inverse reaction, and you get from annihilation of two WIMPs into ordinary particles. Since we could hope to produce these particles through the same process in colliders in the laboratory. And there's been searches for these particles like at the Large Hadron Collider at CERN. None have been found yet, but the search is on. Annihilation provides us another way to search for these WIMP dark matter particles. Because I just told you they are in the halos of galaxies, in the galaxies, they're in clusters of galaxies. So if they annihilate there, they will produce ordinary matter, and we may hope to detect something rarely produced in astrophysics, like antiprotons or positrons, or high energy gamma rays of a very special energy, with single energy. So annihilation provides another means of searching for dark matter WIMPs in galactic halos, like our own galactic halo, or even in the early universe. If they went into the first stars, then they would annihilate and produce gamma rays and other things. In particle physics, one can look at the same process and turn the arrow of time from horizontal to vertical in something that is called the crossing symmetry, and obtain another reaction. In this case, you can do this in chemistry too if you move a reactant from one side of the equation to the other, if you remember your chemistry class. So that's what we're doing. So now we're talking about the scattering of a WIMP of an ordinary particle, which could be a quark inside a nucleus. So the same interaction will produce annihilation, production, and scattering. So we can hope that WIMP particles of dark matter that are floating around in the galaxy come to our detectors on Earth and collide with nuclei. That is direct detection. Another place where the scattering is important is in the large-scale structure. The scattering of particles, of these WIMP particles in the early plasma, determines when they stop sharing the temperature of the plasma, when they don't exchange energy with the plasma anymore. And this sets the scale of the smallest objects in the universe, the smallest galaxies or whatever they are. So scattering is important also to set the properties of the large-scale structure on small scales, so the scale of galaxies. So from the galactic dark matter, as I said, we know that there is dark matter in our own galaxy because we measure, for example, its rotation curve, and we can compute how much there is using our theories of gravity. A galaxy is inside a halo of dark matter particles, and as I said, if we build a detector, we can hope to detect a dark matter particle scattering off a crystal or gas or a liquid that we place in a low background, underground laboratory, because these detectors, in principle, detect any energy that is deposited in the crystal, and one has to shield them from cosmic rays and radioactivity in the lab, in the walls. This is a very hard task. And that's the principle of direct detection. There are many, dozens and dozens of direct detection experiments in the world. Here's a little overview. They cover all continents, America, not in Africa. There's none in Africa. In America, Asia, Europe, even Antarctica, there's a dark matter experiment at the South Pole called DMIs. Where they put the experiment under the ice, so using the ice as a shield. More experiments are coming up, really big ones. They have tons of detector material, of target material. One at Grand Sasso called Xenon 1 ton, one in Slow Lab in Canada is a super CDMS, and one at the Homestake mine in Lead, South Dakota. It's called LZ. And Europe has ideas for ton-scale experiments too, Eureka, Darwin. This is a very active field now that has been financed by National Science Foundation and the Department of Energy. The name of the game is discriminate against the background. I said everything that will deposit energy is going to be a nuisance. And the clever way of doing it is to combine two ways in which the energy is shared once it is deposited in the detector. So some of the energy may go into crystal vibrations of phonons. Some of the energy may go into ionization. And so by looking at what fraction goes into ionization, what fraction goes into heat, the phonons, one can differentiate if the particle that hit the detector had a charge, like an electron or an alpha particle, or was neutral, like a neutron or a WIMP. Rejection levels are very high, about 10 to the 6, 10 to the 7 at this moment. This shows the progress of these direct detection experiments. As you see the year on the horizontal axis, starting in the late 80s, and now here we are today, 2015 already. And this is represented by the cross section, which is a measure of the probability of scattering of a WIMP with a target nucleon. At the top is 10 to minus 40 centimeters square cross section. That was the first experiments at Homestake. They were not dedicated experiments. They were looking for beta decay, double beta decay, and they just used the same detectors to search for dark matter. They were the pioneering ideas. And then you can see that there's a series of lines of different slope, and there's a change of slope every time a new technology was introduced in the field. So at the beginning, there were just so-called bolometers that would register ionization. Then people used cryogenic detectors, having discrimination between two things, heat and light, or heat and ionization. And finally, this other change of slope is moving to noble liquids, liquid xenon and liquid argon. And that produced another improvement in the slope of the capabilities. So we're now down to 10 to negative 4 to 6 centimeters square in cross section. That's a zepto level for cross sections, zeptobar in particle physics. This is what the first dark matter experiment, direct detection of dark matter experiment would do in 1987. First paper using 800 gram of germanium ionization detector is typically what one observes. There's energy deposited in the detector here in keV, 20 and 100 kilo electron volts. And here is the count rate. And you can see radioactive lines. And what one is looking for is a spectrum of this, roughly the shape, the blue line. Sort of what we expect from a naive and simple velocity distribution of particles in the galaxy. So you see, it usually is in the background at low energy. And usually that is where a lot of new claims for detection come. The question really is that a new signal is just some background that wasn't accounted for near the threshold of the experiment. So here we have 1 count per keV per kilogram per day, give an idea. And the goal of these experiments would be to have something that counts only WIMPs and nothing else, but that's a Platonic ideal. So here's Who's in Chicago. And this is a bubble chamber, so when there is an energy deposited, there's a little bubble created. And what I was looking for is just a single bubble. Nothing like that. That's just an ideal. This shows the progress of background reduction. So we were up here about, this is again events per kilogram day keV. So we were up here at the beginning. And nowadays, with the Lux experiment, we are a factor of 1,000 better. The next experiment, like LZ, is expected to arrive to decrease the background by another factor of 100, and we'll be able to detect neutrinos coming from the sun. So that's the level of sensitivity. There's a small detector with ton is not very big. A ton of xenon is it fits on this table. This is very heavy, with high density. So that's the current status. They're really doing well. On the right, you see the neutrino experiments. They're dedicated neutrino experiments on the right. So a lot of progress. Again, the problem is that the background. So here's an example of the expected WIMP spectrum, about 1 event per kilogram year for a cross-section where the experiments are now. And it's a 20 GeV mass, 20 times the proton mass, and at a reachability of these days. And that's what one expects. For comparison, here's a radioactive spectrum of a banana. Again, is about 100 events per kilogram second. So that you have to compare. So this is 1 event per kilogram year. This is 100 per kilogram second. So this is what the current experiment. This is the reach of the current experiments on the left. So now this gives you a better idea of how good these experiments are in rejecting background and how sensitive they are. So no bananas in dark matter laboratories. That's the forbidden fruit. Confusion of the mind. After we have all these experiments, it's not clear what they actually see. Some claim to have seen evidence for dark matter particles. Many years ago, 1997, the DAMA experiment, DAMA stands for dark matter, showed that they observe a modulation in their detected rate with all the characteristics expected for WIMP dark matter. And they've been claiming that with better detectors all along. They have changed their detector, they still see this modulation. It's expected because the Earth goes around the sun. It's a very simple reason why we expect this modulation. So imagine that the particles are coming to the solar system from some direction, say to your left. That's where the sun is moving to. So the particles are coming from the opposite direction. Now the Earth goes around the sun, and in a certain month is going together with the sun, so there's a higher wind of particles, and 6 months later is going in the other direction. Is if to subtract the velocity, so there's a lower wind of particles, and then it repeats every 6 months. That's why we expect a modulation with a period of a year when we search for WIMP dark matter. The DAMA collaboration was alone in this for many years, until 2011 actually, in 2011, when the COGEN experiment, a germanium detector, claimed to observe a modulation with very little statistics. But the modulation was compatible with DAMA. They had a fire. They rebuilt the detector. Maybe they see modulation still. Other experiments claim to have observed dark matter not through a modulation, but just because they have extra events they cannot explain. That's risky, because it could be background. Some form of background they didn't know about. But there are claims around. Other experiments say this is all wrong. Here's a direct comparison of the germanium COGEN detector with a germanium CDMS detector, so same kind of material, looking for the same effect, the annual modulation. In orange, the COGEN claim of a modulation. In blue, the CDMS refutation of the modulation. CDMS claim there is no modulation.
Are the cogent and DAMA modulations in phase?
Yes, because the cogent are the very little statistics, so to within the error bars, they are in phase. There's another problem that has been propagated, especially in the press. The biggest experiments using liquid xenon or lux are very sensitive, or believed to be very sensitive, should see some events if the DAMA modulation is due to WIMPs, but they don't see them. They should see hundreds of events, but there's none. Only a few, couple, which are attributed to background. That's a serious problem. However, there's a lot of theory that goes into this because DAMA uses a sodium iodide crystal, while the liquid xenon experiments, of course, use xenon. And the physics of dark matter could be different for sodium iodide and xenon. So what enters into this? How can one try to solve it? The event rate in such kind of experiments is a product of three factors: the detector response, the particle physics, and the astrophysics. So we have a dark matter particle scattering off a nucleus, and the nucleus is going to record. The detector response is the answer to the question, is a nuclear recall detectable? Because you may have a nuclear recall in the detector but not be able to see it, to observe it. Things like the counting efficiency, the energy resolution of the detector, the scintillation response, how much light you see if you're looking at scintillation light, all affect the probability of detecting an event that occurred in the detector. That can be all bumped into this to a function, a response function that is exactly this probability given a detector given an event with recall energy E sub r. What is the probability that it is actually observed? In general, with some other energy E. If some energy is lost in the observation process. A common model for this response function is a Gaussian. Some mean value that is a quenched energy, some quenching factor, with some standard deviation equal to the energy resolution. This is just a common model. There other experiments have Poissonian statistics, so they use better models. People have tried to measure the quenching factor, and it's hard to find consensus. So here is a review several years ago. The situation is getting better now. Of the quenching factor in germanium, and you see that the data points are all over the place. The theory is no help. In blue are two lines of the same model with a different value of one of its parameters, and a lower value of the parameters seem to fit the higher energy quenching factors. Another value seems to fit the lower energy quenching factors. We don't really understand this, in terms of models. There are now, with the pressure of what is happening, there are now experiments that are measuring these quenching factors better. So it's a hard thing to do. Well, we're getting there. Like, for example, here, this is a quenching factor for xenon. It's called LF, some other name, but it's a quenching factor. It's called light efficiency factor. And there are new measurements down to 2 keV nuclear recall. And a lot of controversy. The people in the field that talk a lot about, we don't know this quenching factor down here where it is important, 2-3 keV. That's really important because that's why we spec the WIMPs. We don't know how much it is, and they fight with each other at conferences. The other factor is the particle physics. What force couples dark matter to nuclei? Dark matter could couple to the nucleon number density, could couple to the nucleon spin density, or who knows what, even the magnetic moment of the nucleus, who knows? This is all parameterized by what is called the differential cross-section. So this is the cross-section divided by the recall energy. And there's some factors that come in just from theory. And this cross-section could depend on spin, Could not depend on spin, could be electric, could be magnetic. The plots I showed where everybody is fighting have a very simple cross-section called spin-independent. It's built in this way. There's an interaction of the particles with protons, with some effective coupling Fp, with these 4 particle vertices, and then interaction with neutrons called Fn, and then their nucleus is made up of protons and neutrons. You add them up coherently, take the square of the amplitude, and then put some form factor, because the nucleus has a certain density profile, and this is the formula that everybody uses for comparison of the experiments. It's a very simple model. So one question that arose is, maybe the cross-section is different, and when we go from sodium iodide to xenon, it's another story. There's no problem of incompatibility between the experiments. There's another example of spin dependent, the same kind of story. We have some nuclear form factors, we have some effective interaction terms. The third factor is the astrophysics. How much dark matter comes to Earth? Now, never mind that we actually know the galaxy at a scale of 100 parsecs or so, and we have to go down 12 orders of magnitude to get to the solar system. That's already a huge factor, but suppose dark matter is somewhat smooth. Even after that, the big problem is that we don't really know the velocity distribution of the dark matter. We don't have a direct probe of that until we detect the dark matter. So let's bump everything into this astrophysical factor that contains the local density of dark matter particles and their velocity distribution. And this is actually an integral over the velocity distribution, counting all the dark matter particles that can impart our given Recall energy. So they need to have a minimum speed in order to do that, because they need to have a minimum kinetic energy so they can transfer it to the detector. The annual modulation that I've been talking about is in this astrophysics factor. It's, we just do a Fourier analysis in time of the astrophysics factor. Pick the first term, we make cosine with some phase. And this omega is the frequency corresponding to 1 year for the motion of the Earth around the Sun. So we have a constant unmodulated signal, the first term, and the modulation amplitude. That's in the astrophysics. And in the plots I showed you, the astrophysics is extremely simple, even simpler than the particle physics. It's the spherical cow model of direct dark matter searches. It's a Maxwellian distribution that is truncated at the escape speed of particles from the galaxy. So when they're going too fast to be trapped in the gravitational potential. So all these assumptions go into these plots. The cross-section versus the mass, showing the current limits here from various experiments, since lux is dominantly at higher masses, claiming the exclusion of modulations like DAMA, which are up here, or CORGEN, which is this yellow dot, claiming the exclusion of other experiments like CREST to CDMS. Ultimately, all these detectors will see neutrinos from the sun, which is down here, the atmosphere. So that's the situation. And now something happened in the past year. And I want to tell you about it. That's the treason and murder. So DAMA modulation doesn't need to assume anything about the particle physics. They don't care. You don't need it. They're just counting events and they modulate. That's all. They don't need to know the cross-section. So they can do, power spectrum analysis. You could study the phase. Here's a periodogram. So the year is folded over and over again. So you can see, for example, in green, a reference energy band where there is no modulation, and in red, the energies where the modulation is detected. So accumulating data with the same phase, this is what you see here, you clearly see modulation, statistically undeniable. It's a 9 sigma evidence for modulation. There have been a lot of explanations, a lot of criticism of this, and none has held up to now. All the criticisms have been rejected for a reason or another. The first idea is everything modulates during a year. But that's too naive. You have to show that it modulates with this phase and with this amplitude. That's harder. And that's where all the explanations up to now have failed. It doesn't mean that this modulation is due to dark matter particles, but it means we still don't know what causes the modulation. As I said, it's a model-independent analysis, and here you can see the analysis of the phase. Here you can see the modulation amplitude is clearly different from zero at an energy of about a few kilo-electron volts. Yes?
So with these experiments, what is their, I guess, assumption on the distribution of WIMPs within the solar system and the galaxy?
None in this. This is what I'm talking here. This is model-independent and a modulation result. No assumption here, except that that there is actually no assumption at all here. No assumption at all. So they measure the phases. This is like this. Here you can see you do this Fourier decomposition. So you get a cosine term and a sine term, and in part one versus the other. So you can figure out the phase. There's absolutely nothing here. No assumption. Then you can go back and ask, can I explain this with some, what kind of velocity distributions do I need to explain this? And it appears to be that the spherical, the Maxwellian distribution with the motion of the solar system explains this. So the phase is correct, the amplitude is correct. So what we would expect naively matches what they observe. Very puzzling. That's the confusion. There's a problem with these collaborations. People have requested to see the data to do some independent analysis since 1997, and the DAMA collaboration has consistently refused to share their data. Nobody ever got an answer of why they refused to make the data public until last summer. And finally, at the Identification of Dark Matter conference in Amsterdam, Pierluigi Belli, who's one of the spokespersons for the collaboration, gave an official statement to the question, when are you making your data public? Public? What does it mean? It has been very useful that the data are made public. The Cogent collaboration also observed a modulation, as I mentioned, and they made the data public, and especially to create a precedent and hope to force DAMA into making DAMA data public. So here's Cogent with all the public data, 3.4 years of Cogent. They see something, best fit phase is consistent with DAMA. They do a lot of analysis. 4 or 6 times larger amplitude than one would expect in some spherical cow model called the standard yellow model. Fine. But since the data are public, other people went and reanalyzed the data and found this. No significant modulation. So here are some statements. The Cogent region of interest results from a biased analysis and has no statistical meaning. There's another one. The likelihood gets worse when including a WIMP component, either as a standard yellow or Sagittarius-like stream. This is Chris Kelso. You might know. But it's worse. This is not just Kelso. This is Colliard, the Cogent leader. So something happened in the modulation paper. This is the modulation on the archive, the 24th of January, 2014. Maximum likelihood signal extraction method applied to 3.4 years of Cogent data. 3 days later, 27th of January, there's a new version, and me and my collaborators have read it completely from beginning to end and couldn't find what is different. And finally, we used grep on the text file. The author list is different. The leader of the collaboration dropped from the author's list, together with Fields, who is in this other paper. Treason. Told about Quest. Quest detected some excessive events. They didn't know what they were. They upgraded their experiment. And they ruled themselves out. Except in a tiny region here that somebody noted. But the new upgraded experiment is incompatible with the previous experiment. There is no extensive events in Quest, not anymore. This is the murder. However, things are looking bright. As Nietzsche said, the German philosopher Nietzsche, that which doesn't kill us makes us stronger. And we have learned a lot in the process of comparing all these experiments. So first of all, the experimental groups have becoming more serious about measuring their sensitivity, about calibrating their experiments. They have devised difficult techniques, but they're working now, so they get better calibrations. The theorists also have come out with new ideas because the standard spin-independent cross-sections didn't seem to work. So they thought maybe we have some other physics for dark matter. Maybe the halo model, the astrophysics of galactic dark matter is different. So two things have come up on the theory side. Use all possible physics models for dark matter WIMPs, and two, use all possible halo models for the astrophysics. Can we do that? Yes. So, all particle physics model. Write down and analyze all possible WIMP nucleus currents. The idea, the inspiration comes from the 1960s, when people knew about weak interactions at the level of the Fermi with four particle diagrams, but didn't know what was fundamental there, like the W boson or the Higgs boson and so on. So what did they do? They wrote down all possible currents, all possible interactions between the neutrinos and the electrons and so on, and the fermions, and by writing all interactions and then going to experiments, they figured out that this was what is called a V minus A interaction, vector minus axial. So that's the inspiration. Let's do the same for dark matter theories. Let's write down all possible currents and figure out which is right. It's a fantastic program. The only difference from the 1960s is that at the time they had particle beams to study weak interactions. Nowadays we don't have a dark matter beam to do the same. But still the program is interesting. So we have a recall spectrum that has a complicated expression but contains the velocity distribution and the cross-section. We're going to play with the cross-section. So traditionally it was a spin-independent case, some formula that had the astrophysical factor and some nuclear form factor in front. Now we can change that. In trying to explain the data, we could modify the cross-section. We could set different couplings to neutrons and protons, what is called idle spin violating. Nothing's violating. Or we can put additional velocity and energy dependence in the cross-section. The idea of isospin violate, correctly, this would be non-isoscalar dark matter. This is nuclear isospin. is an old idea, 2003. It's based on nuclear physics. If you look at the chart of the nuclides, if you plot proton number versus neutron number, you see that the nuclei are not on the line with equal number of protons and neutrons. There are typically more neutrons than protons in a nucleus. And the ratio is about 70%. So the idea is, let's try to have no interaction of dark matter with heavy nuclei like xenon and iodine and tungsten by destructive interference. So this is a coherent amplitude. We have to sum the contribution of neutrons and protons. We can arrange for the coupling to neutron and proton in a way that the total amplitude is 0. If we just choose the ratio neutron to proton couplings to be negative 70%. Maybe a trick, but we don't know what the physics is. So this seems to work because you do suppress heavy nuclei, of course. Is the idea of changing the velocity-energy dependence. People have, in the traditional way, spin-independent case, people have thought of a nucleus as having some charge, the dark matter having some charge, and the heavy mediator particle, like weak interactions at low energy. So the cross-section is basically a constant, 1 over the mediator mass to power 4. If the mediator would be light, however, like a photon, cross-section would depend on the recoil energy, inversely on the recoil energy. But if the interaction would be like a dipole-dipole interaction, all energy and dependence would be different, and velocity dependence would be different. If you have a dipole-dipole interaction, then the cross-section goes as the square of the recoil energy. If for the light mediators, there's a dependence on the relative velocity. So the idea here is to play with this, with the kind of interaction between the particles and the nuclei, in a way to suppress the interaction with detectors that don't see a signal and enhance the interaction for detectors that do see a signal. But this is many specific models, and the program of going back to the 60s is by Wick Haxton, currently at UC Berkeley. So write down all non-relativistic short-distance operators between a nucleus, a nucleon, and a WIMP. Write them out, all down. Then we can compute all the nuclear physics, and we're only left with coupling constants. Do the experiments tell us something? I did an analysis with a postdoc in Heidelberg, Catena, which we wrote down. We used all these operators, all the data available, about a year ago. Wrote down the general Hamiltonian for this, so linear combination of all the operators, and looked for the coefficients. Let's fit the coefficients to the data. That's as we can use likelihood to do this. We can look for correlations. We used both a Bayesian approach and a frequentist approach. I hope you're familiar with this dispute if we use Bayesian or frequentist. So in a Bayesian analysis, this is an example of what happens. In a Bayesian analysis of this operator, when we have more than one coupling to study, we integrate out the other couplings. It's a process called marginalization. So with one coupling on the first column, things look fine. These are exclusion limits that have the same shape as the traditional plots of cross-section versus mass. After marginalization, something bad happens. And what happens is that there's so few data points, so few data, that we're sensitive to what are called volume effects. We're sensitive to our prior probability. In Bayesian analysis, we have to assume an initial probability for our coefficients, and we're extremely sensitive to that. So we're not measuring anything that has to do with data here using a Bayesian analysis. Just our ideas. So we switched to a frequentist method. It's the same data. In a frequentist approach, one does not integrate out the other parameters. One maximizes the likelihood over the other parameters. That is called a profile likelihood. So with one coupling only, things look nice. With all couplings together, still things look nice. So the frequentist method is less sensitive to the lack of data. But our conclusion was we need more data. Always. It was reassuring that we found the correlations we expected. So here is a plot of one coupling versus the other. This is the profile likelihood plotted as in this way as density plot. They all look like boxes, but if you look really close, one of them is not a box. This one has a little dimple there, and that is what we expect. We expected, because there are, in the formulas, there are correlations between the coefficients. I can compute theoretically that you should have a likelihood contour that is an ellipse tilted for this C1, C3 combination. That's what we observed. And we couldn't figure it out until we thought, this is on the left is a log-log plot. This on the right is a linear plot. What does an ellipse look like on a log-log plot? And we did that, we got the black line. So we do see the ellipse. We see exactly what we expect. So this works, the analysis works, we just use for the future. Astrophysics. Can we do all astrophysics model at the same time? Yes. Here's why. As I said, here's the astrophysics again. We are in a galaxy with a dark halo. And we know more or less the density of dark matter where the solar system is. As a function of year, this is a summary plot from Justin Reed of the measurements of the local dark matter density from the 1920s onward. You can see the error bars have shrunk a lot. The recent measurements have small error bars. It's not a factor of 2 like you read in some old textbooks on the subject. It's much less now. So here are two examples, 0.33 with an error bar of 0.2 GeV per centimeter cube, or 0.25 plus minus 0.09. This is from using Sloan Digital Scar survey data. So the error bars are, so we more or less we're happy with the local density of WIMPs. We can live with it. Given all the uncertainties in the particle physics, we can live with this. However, the velocity distribution is very troublesome. We know very little about it near the sun. So if we look at simulations typically, with a few exceptions, do not include the gas, what in astrophysics are called the baryons. Embodied simulations study the gravity of the dark matter only. Cosmological embodied simulations that include the baryons are challenging, but they're coming out now. Hydrodynamic simulations are getting better and better. They're at the level currently of looking at clusters of galaxies, and I expect then in a few years, maybe 5 years or so, they could go down to the scale of galaxies. But even if we don't include the baryons, which we should, because we know that the sun is here and that the galaxy is dominated by baryons where we are, even if we don't include it, we still have problems. Here is the Maxwellian distribution in dashed line, the velocity and number of particles. And even without the baryons, we see that the velocity distribution in simulation is very different. It has peaks and wiggles. So here are some non-cosmological attempts to include the baryons. So like you build a galaxy and then you add the baryons and you see what happens to the dark matter. And what happens here is that the disk of stars and gas is dragging the dark matter. Basically, the dark matter particles that are moving away from the disk are attracted to the disk by gravity. And when they come to the other side, they're attracted to the disk again. So they're going to slowly fall into the disk. That's the mechanism. So there's a population of dark matter on the disk called the dark disk. How much is there? Probably not much in our galaxy because we don't have a lot of activity in the recent past in our galaxy. But still that skews the velocity distribution of dark matter. So we don't really know what the dark matter distribution is. So, and up to now, the approach was to fix the astrophysics, and we have so many choices. The revolution came when it was realized that the astrophysics can be arbitrary. We don't need to go to those plots of cross-section versus mass. We can use a different approach. We can look at the astrophysical factor. Let's study the astrophysical factor as a function of velocity. In theory, will tell us where we should be, and experiments that observe a signal, we place some data points here. Experiments that don't observe a signal, we place some upper bound. This was an idea by Fox, Liu, and Weiner in 2011 that me and Gelmini exploited to great depth. So what does theory predict? If we have a Maxwellian, we expect a Gaussian. If we have just a string single velocity of WIMPs, we expect a box in this astrophysical factor diagram. Here are some examples of analysis done. This is with first Fox, Liu, Weiner, and the other collaborators with Weiner, and Franzen et al. In also 2011. So he has limits from the experiments and claims of detection. And you see sometimes the crosses are below the upper limits, so that's good. Sometimes you can compare two experiments in black and blue and gray and say they're all compatible, as it was a cogent and DAMA. Now, the original idea referred to the recall spectrum, which is not accessible to experiments because of the energy resolution and the various problems. You don't detect everything. There's a response in the detector. And experimenters didn't consider that at all. They said this is a theory game. Until me and Graciela Gelmini rewrote things so that we use quantities accessible to experiments. Then experimentalists started to use this, and there's now students in each collaboration producing plots of this kind, where we don't need to assume anything about the astrophysics. So we have an energy response function in the middle that smoothes out the recall energy spectrum into what is actually observed. However, the math is not hard. You can change variables to the astrophysical factor and the minimum WIMP velocity or speed needed to impart certain recall energy. And you can either integrate over and measure the energy intervals, or you can do unbinned analysis. At the end of the math, you find that the measured rate is a weighted average of the astrophysical factor. So here's the measured rate on the left. There's an integral over the velocity of the particles. There's the astrophysics factor here, eta v. And there's a series of weights, which we call the response function. And the weights will be different for different experiments. Every experiment will be sensitive to a window in velocity space, given by this response function. The formula is a little complicated, but it's computable, and you can plot it. Here are examples. So if you have a 9GeV particle in DAMA, in low energy, then response function I marked it in this thick black line. That's what you expect. On the right is the same particle in CDMS. They're sensitive to different velocities, so 400 to 500 kilometers per second in CDMS, 300 to 600 in DAMA. So in this way, we know what each experiment is probing in terms of WIMP velocity, and we have no assumption on the velocity distribution. So each experiment is probing a different velocity range, and then we will try to combine them and see when they probe the same velocity range, are they compatible? So we can take the data and undo the data, and we're still working on this to make it better. This is the first simple way of getting numbers. And you get these plots which are very crowded, because we put all the experiments, and we can look just at the most stringent upper limit, which is this line at the bottom, and compare it with the claims of detection, and they're not compatible. And we can use modulation claims, they're not compatible. And it's very puzzling, like the unmodulated rate is similar to the modulated rate, which makes no sense. You would have more than 100% modulation. That isn't possible. So we again observe the confusion, but this time without assuming anything about the halo. So one idea, as I mentioned, was, well, we change how many WIMPs come and where they come from, and we fix things. No, this papers show you cannot fix anything. Whatever halo you choose, the experiments are not compatible. So we're hunting for different particle physics. This is for the spin-independent cross-section, and we changed and tried another one, and the non-isoscalar, and we still had trouble. And we've been trying other cross-sections all the way. And only one person of our collaboration, Del Nobile, wrote a paper with some other people because we disagreed, and that he claims he found a model, but we still disagree with him. So that's the current situation. And this method, I mean, for example, currently I am working on this method because it's a very naive way we went to draw these box lines, these data points. There's no statistical number associated. There's no confidence level associated to these error bars here. So we're actually working on putting a number, like 90% confidence level, or those things. And it's a hard problem. So basically, I've been reading about functional analysis in the past few months, and studying topology and other math to figure out how can we handle this. And finally, I've seen the light, and it requires no functional analysis. So. In the next episodes, DAMA has a new experiment. They built a better detector, bigger, with lower threshold, lower background. Revenge. This is the expectation. They started in 2010. They said they're going to take the data blindly. They will not look at the data until many years later. So, yeah, I was at Grand Sasso. I got some insider news, but I won't tell you. The official line is that don't let anyone into the experiment. Here is me at Gran Sasso preparing myself, disappointed, happy, don't know what will happen. They didn't let me into the experiment. I'm outside the door of DAMA Libra. More things to come. I mentioned giant detectors. So this is the plot. This plot was actually made for the Department of Energy, showing the cross-section versus mass. The reach of the current experiments is up here. And this is the new experiments, like xenon n tons. Why n tons? Because they don't know yet. And Darwin in Europe, and then we reach the neutrino coherent scattering, which was said to be the ultimate limit for this kind of experiments. And this is not true. Let me come back to that. It's not the ultimate limit. All interactions, we're still working on that. So Hackstone proposed the program, but only some operators have been put in, some currents, like low energy, heavy mediator, and so on. And there are many other currents that we need to put into this and do a lot of nuclear physics and compare to data and combine all the interactions with the astrophysics-independent method. It's a lot of work to be done. Now let me tell you why the ultimate limit is not the ultimate limit. So these experiments, like xenon, don't see where the particles are coming from. And the neutrinos are coming from the sun. So if you had an experiment that would be able to tell that the neutrinos come from the sun and the dark matter particles from everywhere, from elsewhere, you could distinguish them. And those experiments are called directional direct detection. There's a lot of R&D in directional direct detection. It is hard to do it. Here's a track of a nuclear recoil in the dark matter time projection chamber at MIT. You can see the recoil started on this here. We get more energy and then ended at the other side. So this is possible, not yet at the energies we want. This track is a very high energy. But there are many groups trying to make it work. The great thing is that only about 10 events are needed to confirm that the signal is extraterrestrial. Because if you know the direction, you can plot your events on the sky. As you know, the sky is going around the Earth. The sun, the stars, they all move around. But the laboratory walls don't. So if you use like astronomical coordinates, declination and right ascension, to plot the direction of the events, those that come from the sky will accumulate in the same regions. Those that come from the lab will be smeared out over the solid angle. And that's the technique. That's why you would need only 10 events. The day these detectors will work at the appropriate energies. And something really interesting can come out, and this is my dream for WIMP dark matter astrophysics. WIMP astronomy. Once we know where the WIMPs are coming from, we can study the dark matter particles for their astrophysics, like with telescopes. So here's an example of what one will be able to do. It's called aberration. Now, the astronomers here are familiar with aberration of light. So that was Bradley in 1725. It was really the observation that the irrefutable observation that the Earth goes around the sun and not the sun around the Earth. This was it, the observation of aberration of light. So Bradley looked at a star called Gamma Draconis, and it is the position of the star as a function of time over a year. Parallax, the motion of the Earth around the sun, creates an effect. If you hold your thumb in front of you and move your head, you see the thumb moves relative to the background. And that is parallax. And the Earth produces this effect too. And that's the blue line. It's the expectation of parallax, because we know where this Gamma Draconis, the star, is on the sky. However, Bradley observed a 90-degree phase difference in the motion. The 90 degrees are there because this effect is due to the addition, vector addition of velocities, or the velocity of light and the velocity of the Earth. As you know very well, there is a 90-degree angle between the position vector of the Earth and the velocity vector of the Earth. That 90-degree angle causes a 90-degree change in the phase. So what Bradley observed is the velocity of the Earth. It's only a 20 arc-second effect. The explanation is on the left. If you're standing with an umbrella and then you start moving, you have to tilt your umbrella because the rain comes from a tilted direction. Same with the telescope. If you're stationary, the light is coming in from one direction. If you're on a moving Earth, you have to tilt your telescope. We can do the same for WIMPs, aberration of WIMPs. It will be a much bigger effect. It's only 20 arc seconds because the velocity of the Earth is 30 kilometers per second. The speed of light is 300,000 kilometers per second. But WIMPs, the ratio is in our favor. WIMPs are much slower. Only 300 kilometers per second versus 30. So the effect will be big, 10 degrees, not 20 arc seconds. With some crude directional detector, this is visible. So here is some plots from a few years ago. This is the WIMP sky in May, and here's the WIMP sky in December. and the crust is where the WIMPs are coming from. It's clearly shifted by 10 degrees. And so that's my dream. That one day we will do WIMP astronomy and discover it is the Earth that goes around the sun. Thank you. He has a question.
So when you say the scattering cross sections, like a spin independent versus spin dependent model, are you talking about the spin, like supposing that the WIMPs have a spin, or just that they see the spin of the nucleus differently?
One has to assume that WIMPs have a spin in that case,
Yeah.
for a spin
So,
dependent cross section.
in that case, like, what would be its? I mean, it should still couple the magnetic fields on at some energy or some scale, right?
A spin doesn't necessarily imply magnetic moment,
Right.
but if they have magnetic moment, it couples to a magnetic field.
Right, okay. I mean, like, if there were, what would be like the upper threshold of its possible magnetic moment? I mean, like, it could have a really...
Yes, I don't have the number with me, but I can give it to you later. But it's one of these studies we made was with the astrophysics-independent method. It was on magnetic dark matter, have a magnetic moment, so I can tell you the number. Yes.
Is there any attempt to do a direct detection for the dark matters that generated in colliders?
Well, that is another kind of detection because the dark matter particles are produced in colliders, and they are neutral, and at colliders one detects charged particles by bending them in magnetic fields or having them lose their energy in a piece of material. So neutral dark matter particles would escape detection at colliders, and the searches are done in a different way, looking for missing energy and missing momentum. So energy and momentum are balanced in the reaction, and maybe there's something neutral that is not being detected. In some theories, which I don't see what the direct connection with dark matter is, but in some theories, there's some long-lived particles which may be friends of the dark matter particles, and you may imagine you can trap them once they're produced, and you can go back 10 years later and try to observe their decay. But let me say this in a better way. Dark matter searchers at colliders do not see the dark matter particles directly. They typically see friends of the dark matter particles, like other particles in the theory that are charged. So that is how supersymmetric dark matter is constrained. One doesn't observe the neutral supersymmetric particle, but one observes one of his charge partners. Actually, one does not observe one of his charge partners. And since the theory connects the properties, one is able to place limits on the supersymmetric dark matter particle. So the collider is a little bit different. It's not direct. So the answer to your question is I don't know of any direct method at colliders.
You can't do it because you're creating so much stuff that would make a signal in a direct detector. So that's why they have to be underground because.
So she's younger. She says you cannot do it, and I'm older. I say I don't know the way. So.
If you have your collider miles underground.
You build the collider on this side of the Earth, and you build the direct detector on the other side of the Earth. You expect like the dark matter come across the Earth and hit the detector.
Like neutrinos.
Like neutrinos.
Yeah. That could happen.
The current cross-section for dark matter from these plots is, neutrinos is minus 30. Is about 9 orders of magnitude smaller, so I don't know how big an experiment you need to do for that. It would be really hard, but I'm sure if dark matter is produced at a collider, somebody will do what you suggest. Yes.
So did I understand you to say you ruled out this idea that there's a difference between the proton and the neutron
Scattering, the minus.
Did I say ruled out?
Yes.
Nothing is ruled out.
Well, with your analysis.
Well, I'm just saying that idea doesn't. Okay, the correct statement is that that idea of different couplings to neutrons and protons does not explain the current experimental situation.
Yes.
Okay, that doesn't mean it's ruled out, because the experiments may be wrong. Yeah.
Well, yeah. I still don't quite understand how your astrophysics-independent approach works. What's the essence of?
What's the essence? Aha, now I can tell you, because you asked this question 2 weeks after I understood. So what we are really doing there, we are probing the velocity distribution. So we are counting how many WIMPs have a certain range of velocities. And each experiment is putting a data point there, or an upper bound. That's what it is. Does that explain it?
A little bit better.
A little bit. It took me a long time to understand that this. I had the intuition this is the case, but now I know it for sure. This is the case. It's some incredible theorem by Carl Theodori in the 1920s, applied to measure theory, and it's a strict mathematical stuff, and that's what we're doing. Still unpublished. Yes.
Help us know a little bit more about the DAMA Libra laboratory and the need for the blind data.
If they would make the data public, other people may be able to have some ideas or test the data in some different ways, plot them in a different way,
Okay.
maybe discover idiosyncrasies in the data.
I thought you were asking a different question. So
Was it a different question?
Is,
Well- Build on my question.
why are the DAMA Libra experimenters not looking at their data for X number of years? Like, why are they hiding?
Yes. Okay.
Showing this cat.
Their leader told me many years ago that one goes one's own way.
Okay.
I mean, they're not doing anything different. They're not doing anything different than what other dark matter experimentalists do. It's just that the time scale is, you don't continuously look at your data as a
Okay,
straight
we
thing.
have-
You wait and you say, okay, the end of my first run is now.
Yeah.
Now I'm going to do a fancy analysis to see if there's anything in that chunk of data. So, are they doing anything different than that? Or
Yes.
they are?
Yes.
So
Okay.
Because, the difference is that all the other experiments, except a few, do not observe a signal.
Yeah.
But DAMA does, or claims, they observe a signal. So they should have the moral attitude of convincing everyone else that it is a signal. It is different. I gave a similar talk at ICHEP, the International Conference of High Energy Physics, and I showed Pierluigi Belli with a statement, and Pierluigi was there, and so were other exponents of the DAMA collaboration, and very happily, at the end of my talk, there was a big discussion, and people telling them, show your data. But I don't know, they don't listen. I think they don't listen. But she's right in some sense. You're right in some sense. I mean, the CERN experiments don't show their data. It's a culture. So,
Well, and a lot of experiments keep their data blind while they figure out how to analyze their Monte Carlo and then publish later.
yeah, but this started in 1997. So.
Yeah, the old data, they should release at least something.
Yeah,
What did the Cogent guys release?
Everything. No. No, what is it? They didn't release everything. The Cogent guys had first pass, they cleaned up the data, and then they released events with their time and energy.
So not raw data. They
Not the raw
released
data.
Processed, calibrated,
Yes.
analyzed data.
Yes. There's not much calibration to do in Cogent. They don't have a good calibration anyhow, so they released the detected energy. DAMA is similar for the energy. There's not much one can do. But the problem with DAMA, they have a gazillion data points, and they just do a likelihood analysis with this Fourier term, and they fit the coefficients.
Do they publish anything about their analysis pipeline or their
Yes, it's all written.
Okay.
Yes, everything is written.
calibrations of their instruments? I mean,
Everything written. And actually,
temperature, changing the-
everything is written. All the temperature. Actually, to their credit, they're the best documented experiment in direct dark matter detection and the most careful experiment in this field. And the biggest one too. That is why the competitors can't really, check what they're doing. They are the biggest experiment, the best experiment, and that's why they're so proud. And they say, "We go our own way."
So if we go online and do a search for Cogent data, we can find something.
Yes. I remember I had to email one Colliard to get the data file, but besides that, I did my own analysis of the Cogent data, found nothing. But I didn't publish. I didn't. Colliard is a friend of mine, so.
Or later
Anyway.
there's left.
You seem so. Okay, we're going to be self-led. Any more questions?
Thank you.